Hello and welcome to the Chemistry Academy. In this video we're going to go over Proton NMR in relation to the Advanced Higher Chemistry course. Proton NMR was actually something I really struggled with when I was learning chemistry, so I'm hoping that over my years of trying to make it make sense to me when I didn't really think it made much sense, I will be able to now help it make sense to you. So the NMR first of all stands for Nuclear Magnetic Resonance Spectroscopy. And it is really, an NMR machine is essentially just a big massive magnet, and it looks at magnetic responses within the atoms to be able to detect what their chemical environment is. So for NMR you're looking at the hydrogen chemical environments, and there's two different types of NMR that we'd look at. We'd look at low resolution, which you can see on the left hand side here, and high resolution that you can see just at my shoulder here. So we're going to go over what the difference and similarities between the two are first of all, and then we're going to have a look at how we identify the different hydrogen environments, and then we'll have a look at how we can interpret different spectra to try and work out what substance it is. Now, one other thing I will point out here is that in your Advanced Higher Chemistry exam you won't always just be given an NMR to use to determine the structure of a substance. You would be given other chemical information as well, so it's kind of like piecing a puzzle together. You will get some questions in the multiple choice that are just on NMR, but if it's in the extended response section and you're asked to determine a structure, you will usually have other pieces of information that will help you solve the puzzle. So if we get started on the low resolution versus high resolution comparison, so if we look at the low resolution first, so low resolution will tell you how many different hydrogen chemical environments you've got, and that's basically just for every absorbance or chemical shift line, that will be one hydrogen environment. So this spectrum here is actually for ethanol, both of them are, and I've indicated here the different hydrogen environments and therefore then what peak they relate to. So we can see that there are three different hydrogen environments within the ethanol molecule: the hydrogens that are on the CH3, the hydrogens on the CH2, and the hydrogen that is on the hydroxyl group. So because there are three different hydrogen environments, we would be expecting three peaks on the NMR spectrum, which we've got 1, 2, 3. The chemical shift, the ppm that shift occurs at, will then tell you the chemical nature of those hydrogen environments. So we could look up the data booklet on the page that's got all the NMR information, and we could see where the chemical shifts were expected to occur. So if we look at the hydrogen on a hydroxyl group in an alcohol, it's down here, so that'd be anywhere between 6 and 1. So if we go back, we can see that that was at 4. So it's a bit of a broad range, but you're just looking for it to be in that area. Then it will also tell you how many hydrogens are in that specific chemical environment. So if you look at what's known as the integral pattern, so that's essentially the heights of the lines in relation to each other, it will tell you how many hydrogens are in that given environment. So we can see here the chemical shift that occurred for the OH is only 1 in height, whereas the chemical shift occurring at 3 ppm is 2 in height. There's the wee integral number next to it sometimes. And then we can see that those pink hydrogens in that CH2 environment, there are 2 of them. And then we can see the shift that's happening at 1, which is relating to the CH3 group, is an integral of 3, which relates to 3 hydrogens. So looking at the ratio between the intensities of the lines on your low resolution can give you the integral pattern, as we call it, and that can tell you how many hydrogens are in those environments that are being identified. If we then look at high resolution, so it too can tell you how many different hydrogen environments you have, because each different peak is representing a different hydrogen environment. So in the high resolution we still have 3 chemical shifts. It will also again tell you the nature of the hydrogen environment, because where the chemical shifts are occurring will tell you what chemical environment it's in. But rather than tell you how many hydrogens are in that environment, it will normally tell you how many neighbouring hydrogens you have to those hydrogens that are causing that particular chemical shift. So this is known as the splitting pattern. The splitting pattern follows the n+1 rule. N stands for the number of neighbouring hydrogens, and so you would add 1 for the splitting pattern. There is a table here of what the splitting pattern is called, and then how many peaks are in that pattern, and then therefore how many neighbouring hydrogens there are. This is something you want to try and remember the names of, because you can be asked about that in the multiple choice question. Most of the time you'll only really get up to octet, you won't really get asked about anything above that. If you do, they would tell you what the name of it is. So yeah, singlet would just be where you've got a single peak, so like this one here. And if I just zoom in so you can see it a bit better, and that means there are no neighbouring hydrogens for the hydrogen that's causing that chemical shift. This one here, that would be called a quartet, because you can kind of see it consists of a peak that's split into 4 parts. The quartet, following the n+1 rule, means that there's 3 neighbouring hydrogens. Just realised that that says neighbouring carbons and not hydrogens. Silly me. So that's how they both work. Now what we're going to do is, like I said, start off by looking at how we identify different hydrogen environments in a molecule, because that's a skill that you need when it comes to interpreting and suggesting what NMR would look like. And then we'll go and actually look at some spectra. So if we go here, you'll see I've got 6 molecules here, all carbon-based molecules. So we're going to look at how many hydrogen environments they have first of all. So if we look at the first one, this one here, this is propanoic acid. So when we're looking for a hydrogen environment, I've got an analogy I often use, where I think of the carbons as a house, and all the hydrogens attached to that carbon live in that house. So all of those hydrogens are in the same house, so they're in the same environment, the same chemical environment. So you're essentially kind of looking at how many different houses you've got, really. So we've got this house at the end here, which has 3 hydrogens in it, so those hydrogens will all be the same. We've then got the next house along the street, which has got 2 hydrogens in it, so those 2 hydrogens are in the same house, so they're in the same chemical environment. And then we've also got this hydrogen that's at the very end of the street on its own in a house, which is obviously not a carbon, but it's just out on its own. So in this one there's 3 chemical environments, so therefore we would be expecting 3 peaks on an NMR. And we could look at the chemical shifts that we would expect and suggest how many there should be. In terms of the integral pattern that we would expect on a low resolution, we would expect an integral pattern of 3, 2 and 1, because you've got 3 hydrogens in one house, 2 hydrogens in another, and then the 1 on its own. So that's the sort of thing you'd be looking at. If we were then looking at the splitting pattern, so these hydrogens that are in this house at the end of the street, next door to them is a house with 2 hydrogens in it, so they have 2 neighbours. That means they would then form a triplet, because they have 2 neighbours next door, and following the n+1 rule, that would give it 3. If we then look at these hydrogens here in this house, so they're neighbours, they've got the 3 hydrogens on the left hand side of the street, and in the house next door there are no hydrogens, so they would have only 3 neighbours, which would give them a quartet. So that this line would end up producing a quartet. Those hydrogens would. Then we've got this hydrogen here. If a hydrogen's attached to an oxygen, it's kind of a bit like the oxygen's a bit like a wall. The hydrogens can't really see past it. So this hydrogen would actually have no neighbours, and so it would give a singlet, because N0 plus 1, no neighbours plus 1, give you a singlet. Okay, so that's how I tend to think of the whole splitting pattern thing, is think about those hydrogens being in a house, and then how many neighbours do they have, like how many hydrogens are living next door to them, either side of the street. So let's go on to the next one. We've got a CH3 group here, so that'll be 1 hydrogen environment. Then we've got this CH2 group, and then we have another CH3 group, but this CH3 group is not the same as the one that we've already coloured in blue. because if we think about their view of the street, their houses aren't identical. So this CH3 group lives next to CH2 group. This CH3 group lives to a C double bond O, so that's not the same. So that means they would, although it is a CH3, they would be a different chemical environment. Okay, so again, we'd be expecting 3 peaks on this one. We'd be expecting an integral pattern this time of 3, 2, 3, or 3, 3, 2, depending on how the shifts come out. And then in terms of the splitting pattern, if it was a high resolution, this house here, I've got 2 neighbours next door, so this one would produce a triplet again. This one here has got 3 neighbours next door, so they would produce, they would produce a quartet because they've got 3 neighbours. These 3 hydrogens here, they don't have any hydrogens living next door, so they would produce a singlet. Okay, so that's a new one, but these ones would just be triplets and quartet. Cool. So then the next one, we've got CH3 group at the end here. So that's 1 hydrogen environment. We've then got a CH2 group, which gives us the other one. Now this time we actually have like a symmetrical street. So if you can see here, this side of the street is identical to this side of the street, which means that this CH3 group is actually identical to this CH3 group because they're like a mirror image of each other. So you want to look for symmetry in molecules when it comes to NMR. So that means those hydrogens would be the same, and then these hydrogens on that CH2 group would be the same as the ones on the other side. That means that we would only actually get 2 peaks on this spectra because there are only 2 different chemical environments. However, for the integral pattern, we have 6 in the blue and 4 in the green, so that would be 6, 4, or it could potentially come out as 3, 2 if it was a simplified ratio. So a lot of the time then people think, well, how am I meant to know how many hydrogens it is? In these questions, you will always have the molecular formula of the substance you're trying to find, and we'll get onto that in a minute. So use the formula to help you know how many carbons there should be. So for this molecule, you would know that there were 5 carbons in it. So if you only see 2 peaks and there's 5 carbons, that means that there's got to be identical houses, if you like. So there has to be some CH groups that are identical to other CH groups, otherwise you're not going to be able to use up all your carbons and hydrogens. So that's the best way to think of it in these particular questions. Then if we look down here at the hydrogen environments, we've got this CH3 group at the end, this CH2 group, and then just this H group here. And again, for the splitting pattern, these carbons here have got 2 neighbours, so that would give you a triplet. These hydrogens here have 3 neighbours, so that would give you a quartet. And then this hydrogen here should have 2 neighbours, so the CH2 group, so that would give you a triplet as well. Moving on to the next one. Sorry, I should have said as well, for this one here, the splitting pattern, it would just be a triplet for these 3 because they've got 2 neighbours, and then a quartet for these ones. So then the next one, hopefully you're getting the idea here. It does seem a bit repetitive, but here we've got 3 hydrogens, and then we've got these 2 hydrogens in their own house, own environment. Now it looks here as well that this molecule is symmetrical, but it's not, because there's this single bonded oxygen here, and that's going to change the electronegativity of these carbons here, because that oxygen is going to be pulling electron density away from them by a different amount than this carbon with the double bonded O is from these ones. So these are different, it's not a direct mirror image. So that means that they've got a different one. So here we would be expecting 4 peaks because we've got 4 different chemical environments. In terms of the integral pattern, we would have 3, 2, 2 and 3. So you kind of get the gist, and then the splitting pattern, hopefully if you go through the houses thing, you'll be able to work that out yourself. And then the last one, we've got this CH3 group on the end, we've then got this CH2 group, and again this molecule isn't exactly symmetrical because there's an OH group on the end here. So we've then got this CH2 group, so those hydrogens, then these hydrogens, and then we need one extra colour for the hydrogen on the hydroxyl. So here we've got 1, 2, 3, 4, 5 colours, so we'd be expecting 5 peaks there, and the integral pattern would be 3, 2, 2, 2, 1. And then in terms of the neighbours, if we'll go through this one because it's a bit different. So this hydrogen here, the purple one, that has no neighbours because, like I said, the oxygen kind of acts like a wall, so you can imagine that's in like a different neighbourhood. This carbon here, these hydrogens here, they are next to 2 hydrogens, so they would form a triplet. These hydrogens in this house here, they have 2 hydrogen neighbours, so they would also form a triplet. And then these 2 hydrogens here, they've got 3 neighbours, so they would form a quartet. And then these 3 hydrogens here have 2 neighbours, so they would form a triplet. Okay, so hopefully that helps you with determining the chemical environments, because the number of hydrogen environments, because that's a key step when you start looking at the NMR spectra, is looking at how many hydrogen environments you're actually expecting to have or how many you actually have. So here we're going to look at 2 low resolution spectra and try and work out what the substances could be. So we have in the one on the left, we've got 4 different chemical environments. On the one on the right, we've only got 3 different chemical environments. So that tells us straight away that these are 2 different substances. Despite the fact that they've both got the same molecular formula, they are 2 different things. Now, like I said, when you are interpreting the NMR spectra in the exam, you will normally be given the molecular formula. So you do have atoms to kind of go off of. So because of the ratio of carbons to hydrogens, it looks like it's a saturated substance, so there's no double carbon-carbon bonds or anything. And we've also got 1 oxygen, which means it's either going to be an ether or an alcohol. It could, with 1 oxygen, also be an aldehyde or a ketone, but if that was the case, they wouldn't have this many hydrogens. Okay, so using the molecular formula and to try and help you work out what type of molecule is also helpful. Normally as well, you will usually have been given an IR spectra at some point in the question, which will help you identify functional groups, which again helps you narrow down what type of molecule it is. So if we just have a sketch out of what these molecules could be, so we've got 3 carbons. If it's an alcohol, it means the hydroxyl will be on the end. If it was an ether, we would have an oxygen in the middle. We could also, as well as having propan 1-ol, we could potentially have propan 2-ol. So I'll sketch that out as well. So these questions do require a bit of sketching out and seeing what fits. Here we've got these molecules. These are potential molecules, so let's look to see if we can work out which one is which in terms of the NMR spectra. So if we look at the number of hydrogen environments, we've got 1, 2, 3. So they're all the same. These are the same, and then these are the same, and then this one on the end's its own type of one. For these ones here, these 3 will be in their own environment, these 2, and then these 3, because none of these molecules have any symmetry in them really. Oh, I've realised I've just drawn the ether twice, sorry, that was meant to be propan 1-ol. Propan 2-ol. 1, 2, 3. And then for this one, our molecule actually does have some symmetry in it. So go back to the highlighter. So the hydroxyl hydrogen, that's one on its own. Then we've got this one, and then we've also got these 2 as being the same, because they are mirror images, those CH3 groups. So if we're looking to narrow down the options of which one's which, the one with 4 peaks has to be the propan 1-ol because it's got 4 hydrogen environments. We can also then check the integral pattern. So the integral pattern should be 3, 2, 2, 1. and we can see that we have a 3, 2, 2, 1. So it fits the same integral pattern. So if we were writing it in an exam, we would say it fits the integral pattern 2, 1, 2, 3 or something, just whatever the integral pattern is on your graph. So that helps us then work out that this is propan 1-ol spectrum. Okay, for this one here, we've got the integral pattern. So we could have 3 chemical environment or 3 peaks in both of these. However, if we look at the integral pattern, for this one it would be 3, 2, 3. For this one it's 6, 1, 1. So we can tell then from the height of the peaks that actually this one must be propan 2-ol, because for the methoxyethane we would have expected a different integral pattern. We also potentially could have been able to tell by the chemical shifts for the OH, the H on the OH, but sometimes it's not as definitive because there is such a wide range for that one, because it goes from 1 to 6. So the integral pattern is probably the best thing to be looking at. Okay, so let's have a look at the high resolution spectra, and we'll see what one of the compounds this is. So we can tell, because it's got 4 peaks from before, it has to be propan 1-ol. But if we just look at the splitting pattern then, so I'll just draw it out again. So if we look at the neighbours that we've got here, so these 3 are, so they've got, I'll just actually colour all the hydrogen environments. So here, this CH3 group, it lives in a house, they live in a house, the hydrogens live in a house next to 2 hydrogens, so they would have 2 neighbours, so they would form a triplet, because 2 plus 1 is 3. These hydrogens in this house here, they've got 3 neighbours on the left and 2 neighbours on the right, so they would have 5 neighbours altogether, so they would actually form a sextet, because 5 plus 1 is 6. These hydrogens in this house here, they have 2 neighbours on the left, and remember the oxygen is like a wall, so that's all they've got is 2 neighbours, so they would also form a triplet. And then this hydrogen at the end here, it's got no hydrogen neighbours because of that oxygen being like a wall, so that would give you the singlet. So then if we have a look at this high resolution spectra, we can see here's the singlet here. I'll zoom in a wee bit. We've got a triplet here, a triplet, another triplet here, and then that's the sextet. If you were able to count 1, 2, 3, 4, 5, 6. Okay, so this, when you're looking at the high resolution, the splitting patterns can tell you like what's next to that substance, so it can kind of tell you, or that group, so it can kind of tell you what groups are actually there. So if you see a triplet, that means there must be a CH2 somewhere. If you see a singlet, that must mean there's like a hydrogen that's like on an oxygen or something that's getting blocked. If you've got the sextet, it means that there's probably carbons in the middle, because you're not going to get a 1 carbon house next door that's got 5 hydrogens on it. It's not possible. And then the triplet again tells you that then there's another CH2 group. So if you were to see that, you would be able to tell that there is stuff, there's something sandwiched in between some things. So yeah, you'd be looking for that. If we then go on to this one, so this is an interesting spectrum, this one. You should be able to tell from the formula that this is benzene, because it's C6H6. But for benzene's NMR, it just does come out as 1 peak, and that's because all the hydrogens are technically in the same chemical environment. Because it's a symmetrical substance, they all sort of have the same view of the street, if you like. So you would actually end up with the integral pattern here of 6 as well. And it does occur at the chemical shift that's relevant to aromatic hydrogens. If you have a look on page 17, you'll see the aromatic hydrogens are these ones here, the 9 to 6.9. You're wanting to, when you're looking at what the hydrogen environment is, you always want to look at what the bold hydrogen is on this page of the data book. That's the one it's representing. So that's the spectrum for benzene. I just wanted to point out it is a bit of, if you ever see any with like a really high peak, and there's not very many peaks in the spectrum, you probably do have benzene. However, you will again be given the molecular formula, so normally you can tell with the number of carbons to hydrogens if you've got benzene there, because you won't have very many hydrogens to play with. This one here as well, again, it's another indication you've got the molecular formula. There's not very many hydrogens to carbons, which means that you've most likely got a benzene ring involved somewhere. There are 4 different peaks here. So there should be 4 different chemical environments, but based on the molecular formula, there's most likely going to be a benzene ring involved, but it's got an O on it, so it's probably going to be an OH potentially, or it could have been a ketone, but if we drew a ketone, we would have found out that we had 1 hydrogen left over. So I'll just draw that so you can see just now. So say we drew the ketone. That doesn't actually work because you can't even make the benzene. Ignore that. So the benzene here, if we look at its hydrogen environments, you've got 1 here that's furthest away from the phenol. That's technically different. Then you've got these 2 that are symmetrical. These 2 that are symmetrical as well, and then the one on the hydrogen on its own. So that should give us the 4 peaks. And again, the integral pattern we would expect 1, 2, 2, 1, which we've got 1, 2, 1, 2. So that fits the integral pattern we'd be expecting for that molecule, which is phenol. One thing you need to watch out for though with benzene and phenol is sometimes the SQA change their mind as to how many different hydrogen environments they're going to put in the molecule. So this is just something you need to be aware of if you are given a question. Sometimes you just have to kind of make the NMR fit what the options they've given you. So if you've got molecules to choose between and none of them really seem to fit, it might be that in the phenol ring they've decided that some hydrogens are contributing to the same chemical shift. So as well as having the 4 different ones, they can also sometimes class these 3 as being the same, and then these 2 as being different, and then lastly this 1 being different. So that would give you the 3 shifts, and again the integral pattern of 3, 2, 1, so we can see the 3, the 2 and the 1. For this one here, in this one they've decided that all 5 of these are the same, and this one is just the different one on its own. So again, this peak would be 5, and this one would have an integral of 1. So that's just something to watch out for when it comes to phenol or benzene rings. The goalposts can change for how many different hydrogen environments they're classing it there to be. Okay, so for this one here, we've got again a molecular formula, and we've got a low resolution, high resolution spectrum. So we're just going to see if we can work out what molecule it actually is. So again, we've got the molecular formula, which gives us a good starting point. So it's got 1 oxygen, which means the molecules we know of that only have 1 oxygen would be an alcohol, an ether, an aldehyde or a ketone. It's unlikely to be an aldehyde or a ketone because it's got 2N plus 2 hydrogens to carbons, so it's most likely going to be a saturated alcohol or an ether. So if we just sketch out some alcohols with 4 carbons, so we've got butan 1-ol, and we've also got butan 2-ol that we could have. Sorry, I get to the point where I get fed up of writing hydrogens. And then we could also have an ether. So if we do a symmetrical one where it's ethoxyethane, and then we could also have methoxypropane. So again, for these, a lot of the time you do just need to sketch out potentials and then see what fits the spectra you've got. So don't be scared to jot some ideas down. It's very unlikely you'll be able to come to your final answer on these without jotting some ideas down. So first thing to look at is the number of hydrogen environments, because that usually helps you narrow down your answer very quickly. So for here we've got, oh, why is this not working? We've got 1, 2, 3, and then we've got these two, which are different from these two, which are different from these two because they're all different distances away from that OH group. And then that's this one. Oh, that's not a very good yellow colour, is it, Kimberly? That one on its own, hopefully you can see that. So that's obviously got too many hydrogen environments to be our molecule because we're looking for only two because there's two peaks. So because we've got 4 carbons and there's only 2 peaks, that suggests to us there's maybe some form of symmetry in our molecule. So if we look at all our other options, none of these are symmetrical except for the ethoxyethane. So if we look at the hydrogen environments in that, we've got these 3, these 2, and then we've got the symmetry, the mirror image. So then that means these 2 are the same as the other greens and these 3 are the same as the other purples. So that would give us our 2 hydrogen environments that matches, and then in terms of our integral pattern we would have 6 and 4. So we just want to make sure that that line looks like it's a third bigger than this one, which it does. So that fits the integral pattern 6-4 or 3-2 if you like. Also for the high resolution, we can see here that this is a quartet, so that's next to a CH3 group. And then this is a triplet, which means that's next to a CH2 group. So we can see that there's a CH3 with a CH2, and it's just a mirror image of that across that ether group there. Okay, so that's how you can kind of determine what molecule you've got, is by looking at the spectra. But the key is to try and first of all identify what type of molecule you're even looking for, and then look at how many hydrogen environments you're looking for. And that's usually the easiest way to kind of go about it, in my experience. So that brings us to the end of this. I hope that was useful. It's probably ended up a bit longer than I had expected it to, but like I say, it is a bit of a tricky topic. It does just take a lot of practice. Just a reminder, if you are looking for additional question materials on things like NMR and lots of other topics within the Advanced Higher Chemistry course, you might want to consider joining my Advanced Higher Revision Resources Google Classroom. So if that is something you're interested in, I will post a link in the comments below for you to access that. Yeah, if you found this video useful, please give it a like. Don't forget to subscribe, and I will see you again soon.